a lone pair of electrons. Carbanions have a lone pair of electrons and negatively charged, and they are rich in electrons. Okay, they can donate the electrons. So let me give you an idea about carbanions. I'll take the next page, that is better. Carbanions. Negatively charged, carbon species. Okay, they have negative charge. Have a pair of electron in a single orbital. Have a pair of electron in an orbital. So they have got a pair of electrons in one orbital. And see, it is something like this. You have 3 hydrogen. See how we draw the electrons, the 3 bonds to have 3 hydrogen atoms. And now you have one orbital which contains a pair of electrons. And so, since there is a pair of electrons, it will be having a tetrahedral geometry. Tetrahedral geometry. Because the pair of electrons will act just like a bond. Pair of electrons will act as a bond, and that will be pointed towards one side, right? And you have to remember this, they can equilibrate into this form. See here, this can go back, all these can go back. That is, see here, this can fold back. Folding, that is, they will come first straight. See this, it will become straight by bending it backwards. And at that moment, you will have this orbital in this fashion with the electrons equally distributed. Then see here, it gets reversed up. So this is just an intermediate stage or a transition state. See here. Now what happens? The hydrogen bends upside. This hydrogen also bends to the upper side, and here is this hydrogen. And see, the orbital has inverted. See that. Now they don't pair. So this is in equilibrium. This is in equilibrium. It is not that it's always like this. There is an equilibrium between this form and this form. And so what an electrophile can react either from here or from here. That is possible. Okay. So once a carbanion is formed, the carbanion can be attacked from either side because there is an equilibrium. This type of equilibrium is there. Okay. So this is an internal rotation, inversion. Okay. It's something called a pyramidal inversion. You can call this a pyramidal inversion. Pyramidal inversion. So, and that is how you generate the geometry. So you have a positive. So carbanions are positively charged. They have a pair of electrons, and these electrons can be used to form a bond with other species. Now let us see how you can make carbanions. formation of carbanions, formation. See, this is nearly sp3 hybridized. Carbanions are sp3 hybridized. You can see just like your methane. Instead of one hydrogen, you have a pair of electrons. So very similar to that of methane. Now formation, you can generate this from Grignard reaction. Grignard reaction or organometallic compounds. Grignard reaction. You must be knowing what is Grignard reaction. Grignard reaction. Can anybody write what is a Grignard reaction? Try to write in your paper an example of a Grignard reaction. This reaction you must have already heard. Why don't you try? Anybody? Just write. How many of you know it? Check your answer now. If you have already written, just check your answer. The reaction is an alkyl halide RCl reacting with magnesium in presence of ether solvent, dry ether. There should not be any water in the reaction mixture. There should not be any water. Now you react this with in magnesium, dry that. Remember, dry this used as a solvent only. This will form RMgCl. See, an insertion bond, insertion reaction. Magnesium is getting inserted between these bonds. And you can see here, this magnesium is electropositive, and this is electronegative. Carbon is more electronegative than magnesium. And therefore, if you are breaking this bond will always break towards the R. This bond will always break towards R only, so that you get R minus and MgCl plus. And this R minus is known as a carbanion. So that is number one. Number two, you can prepare this by lithium reactions. Lithium reactions. For example, if you take N-butyl lithium, and say you take phenyl bromide, C6H5Br. You can prepare phenyl lithium. See, a lithium bond is formed. And lithium is more electropositive, and that very clearly tells you that this is going to be negative, this carbon is going to be negative, and lithium is going to be electropositive. Okay, so any negatively charged carbon you will call as carbanion. Clear? So this is the reaction of this is a method of formation of carbanions. Okay, so very good example. You can see what you have to see is whenever you break a bond, make sure that the bond is getting broken to more electronegative atom. Magnesium is less electronegative than carbon. So this bond will get broken only towards the carbon side, and that is why you get R minus. Okay, so that is the method of formation. Let me check what. Yes. Now I told you ether is used as a solvent. Instead of that, you can have THF also as a solvent in Grignard reaction. Okay, THF is also a solvent in Grignard reaction, and THF is having this structure. See, this is THF, tetrahydrofuran. Tetrahydrofuran. Okay. It's a 5-membered ring with an oxygen. That is also used as a solvent. So then lithium bromide, you can prepare N-butyl lithium and react with C6H5Cl. Oh, yeah, that is one of the method I have given you. Yeah, N-butyl. This gives you a N-butyl lithium. Okay, lithium is reacted with N-butyl bromide. You will get N-butyl lithium plus lithium bromide. So that is also a method of making lithium reagent. So here N-butyl will act as an nucleophile, NBU minus, and lithium bromide. Okay. Next, you have you can have copper and cadmium compounds, organometallic compounds. See, copper and cadmium organometallic compounds. That also will generate carbanions. Organometallic compounds with copper and cadmium. We'll discuss this in detail when we are coming across certain name reactions. Now, other examples of the carbanions, these are other examples. See here, this is CH3, CH minus NO2. CH3, CH minus NO2. That is another carbanion. I'll explain to you the details of that. See here. Why is that? Now, one thing is that all these has to be stabilized. Now, see here. Think about this carbanion with NO2. Now, you should have a mechanism by which this negative charge can be stabilized. Only in such cases you can form stable carbanions. Now let me write the resonance structure of this. Okay, see how you are writing the resonance structure. Resonance structure means delocalization of charge. Resonance structure is delocalization of charge. What is the meaning of delocalization of charge? Spreading them throughout the molecule so that it is not getting concentrated on any particular atom. Spreading the charge. So let us see whether we can spread this charge from this negative charge from this carbon to other side of the molecule. See here, I will draw the full structure of NO2 here, which we have already done. I'll write the NO2. We have done it. Will you write the NO2? You have a double bond, a single bond with 3 lone pair of electrons and a negative charge. And nitrogen has got 4 bonds, and therefore it gets a positive charge. Okay. Now see how we do it. This attracts here to form a bond. It forms a bond here. So see here, we got a double bond. And the nitrogen is still there. But in that case, the nitrogen will have a 5th bond. Already there are 4 bonds. The nitrogen will have a 5th bond, which you will never appreciate. I have already told you nitrogen cannot have more than 4 bonds. Nitrogen can never have more than 4 bonds at a time. If it is forming a 5th bond, some existing bond has to break. Okay, so this is coming here. You have 2 choices. You can break this way, you can break. The lower oxygen you can break. But the problem is you cannot break a sigma bond during a resonance structure formation. Okay. So during resonance writing, during the presentation of resonance structure, sigma bond should not be broken. Sigma bond should not be broken. Sigma bond is a single bond. Okay. If you have a pi bond, it will be two bonds. Here only sigma bond means you should not break a single bond. Because see, if you are breaking this bond, the oxygen will go away. And molecule get decomposed. So when a bond is appearing here, the second bond will disappear from there to the oxygen. See how it is getting stabilized. See, you have the negative charge getting transferred over to this oxygen. The negative charge is getting transferred over to this oxygen, and this oxygen remains the same. Already there are 6 electrons with a negative charge, and the positive charge of nitrogen is still there. It is still there. Now see, on this side you have 1 positive, 2 negative. And here also you have 1 positive, 2 negative. See that? So the negative charge is spread here. Now the negative charge now it's everywhere. The negative charge is spread between the between the carbon and the 2 oxygens of the nitro group. So it is not getting concentrated. That is the meaning of writing this. It is not getting concentrated on this arrow. So this is what is meant by resonance writing. So resonance will give you stable compounds. Resonance always gives you stable compounds. Similarly, if you have a CN group, 1, 2, 3, triple bond attached to R. This also can generate a good nucleophile. Okay, this also can generate a good nucleophile because the lone pair of electron which you are generating from here can attack the lone pair of electron which you are generating can be delocalized over to this CN group. Say for example, see here, this lone pair I'm shifting here, and this is getting shifted. Why? Because nitrogen is more electronegative than carbon. Nitrogen is more electronegative than carbon, so the triple bonded electrons getting transferred to the nitrogen. So this also is delocalized. Delocalized carbanion. Delocalized carbanion. Now suppose look at this carbanion. Okay, if you react this with sodium, if you react this compound, diethyl malonate, this is called diethyl malonate. So diethyl malonate, if you react this with sodium, you will get a carbanion, OET, the sodium salt of this diethyl malonate. And see here. O sodium salt. And this sodium salt will be having a lone pair of electrons. See, this can be delocalized. See, you can spread this charge. See here, you put an arrow here. That means that this lone pair of electrons is converted into a bond, and this can go here. It can form an anion. So, what is the resonance structure? Let us write the structure. I can write the resonance structure. Resonance structure will be stabilizing the species, anion. OET. O minus, double bond here, OET. Okay. Now see this, the other carbonyl group also can stabilize it. See how you do it. Just reverse it. And see this goes here, and this goes here. Okay. So this is how you stabilize this anion. And you can see anion flanked by electronegative group, electron withdrawing group. Carbanions having electron withdrawing groups. Electron withdrawing groups. Carbanions having electron withdrawing groups are quite stable. Stable. Okay, having electron withdrawing groups are stable. So these are the electron withdrawing. Which are the electron withdrawing groups? NO2, Cn. Both examples we have seen, and then COOET. Right? COOET. That is also electron withdrawing, because the proton here is removed and this anion is delocalized. So this is these are the reactions of carbanions, or rather method of formation and carbanions. Now let us see what is geometry I have mentioned. Now let's look at the free radicals. Look at free radicals. What are free radicals? Free radicals are species which are neutral and contain one electron in the inner orbit. Okay, it contains an odd electron. Free radicals free radicals contain an odd electron. In that species. You can see earlier we have seen carbocation, no electron, carbanion, 2 electrons, free radical, 1 electron. Okay, and geometry of free radical will be almost like very near to sp2 hybridization. Nearly sp2 hybridization. Okay. Nearly it is sp2 hybridization. And the free radicals are formed by the homolytic bond fission. Now, what is homolytic bond fission? A bond is getting broken and the electrons are taken back by the atoms. See here, look how I'm drawing the bonds. We have discussed already. Now we'll see this. See here. One electron goes to one chlorine, and the second electron goes to the second chlorine. That means you generate two Cl dot. And remember, this cannot be done in the absence of H nu. H nu means light. So this is a light catalyzed or initiated reaction. This is a light initiated reaction. Now you can see, I will show you one more where without the light, in presence of one peroxide, in presence of one chlorine atom, methane can form a methyl radical. Now, what is methane? This is methane molecule. This is what is it? So, no, okay. Now this is your methane. See, another method of forming a radical. In presence of one radical, you can form another radical. See here. This chlorine electron and one electron from this hydrogen gets shifted here. And the second electron of this carbon goes there. So what you get is okay, and you have one orbital with one electron. Orbital with one electron. See H, and H. Okay, so now see you have used one plus HCl. Oh, what did you put? 2 electrons. Sorry, only one electron is there. So then, so you have generated a new methyl radical. This is a methyl radical. Okay. Methyl radical. So this is a method of making, and many times photochemical reactions are having free radical mechanisms. In photochemical reactions,